Hello everyone and very welcome to the presentation of our paper entitled Domain Adaptation for Medical Image Segmentation using Transformation-Invariant Self-Training. While supervised deep learning approaches have yielded satisfactory performance in semantic segmentation, their performance is heavily limited by the label training dataset distribution. Indeed, a network trained on a dataset acquired with a specific device or configuration can dramatically underperform when evaluated on a different device or conditions. Overcoming this entails new annotations per device, a demand that is hard to meet, especially for semantic segmentation, and even more so in the medical domain where expert knowledge is essential. Self-training techniques based on pseudo-labeling have been shown to be highly effective for semi-supervised domain adaptation. However, the unreliability of pseudo-labels can hinder the capability of self-training techniques to induce abstract representation from the unlabeled target dataset, especially in the case of large distribution gaps. Since the neural network performance should be invariant to image transformations, we look to this fact to identify uncertain pseudo-labels. Indeed, we argue that transformation-invariant detections can provide more reasonable approximations of ground truth. Accordingly, we propose a semi-supervised learning strategy for domain adaptation termed transformation-invariant self-training. We validate our approach on 3 cross-device or site datasets for 3 different modalities: cross-site and device instrument segmentation in cataract surgery videos, cross-device IR fluid segmentation in retinal OCTs, and cross-site prostate segmentation in MRI images. At training time, images from the source dataset are augmented and pass through a segmentation network by which the network is trained using a standard supervision loss. At the same time, images from the target dataset are passed to the network. We feed 2 versions of each target image to the network. First, the original target image, and second, its non-spatially transformed version. Once fed through the network, the corresponding predictions can be computed, where sigma is the softmax operation. We then define a confidence mask ensemble as the element-wise multiplication of highly confident predictions from the original and the augmented target images. Indeed, the confidence mask ensemble encodes regions of confident predictions that are invariant to transformations. This mask is utilized to filter out unconfident predictions from the pseudo-ground truth mask. The training loss combines supervised and pseudo-supervised losses with a gradual increase in the weight of pseudo-supervised loss to reinforce training on transformation-invariant highly confident predictions. According to the quantitative results, our proposed TSD achieves a significant relative improvement in DAS score compared to naive supervised learning. It can also be perceived from the results that TSD has the most consistent performance over different folds compared to the alternative methods. This superior performance is qualitatively compared in this figure. Ablation studies confirm the effectiveness of TSD regardless of the pseudo-labeling threshold and the number of label training images. If you have any questions or suggestions, please don't hesitate to contact us. And thank you so much for your attention.